So imagine trying to hear a whisper from across an entire continent. Now, what if that whisper was coming from space? How in the world would you build an instrument sensitive enough to catch it? And where would you even put it to get away from all of our planet's noise? Well, the answer takes us to one of the most hostile environments on Earth in a story of extreme science that honestly required even more extreme engineering. Okay, let's dive right in. Every single time lightning strikes anywhere on the globe, it doesn't just create a flash and a bang. Nope. It sends out this little whisper, a natural radio signal that ripples all the way out into space. Our planet is just constantly humming with this energy, a whole symphony of natural phenomena. Scientists, of course, have a name for these signals, ELF, VLF waves. That's for extremely low and very low frequency. And they're not just random noise, they carry secrets. You get these phenomena with these amazing names like chorus and auroral hiss, and they ride these waves, giving us these crucial clues about what's going on in space, that intricate dance between the sun and our Earth. Now, to hear these incredibly faint signals clearly, you have to get away from all of our man-made noise. And the absolute best place to do that? Well, it just so happens to present one of the biggest engineering challenges you can possibly imagine. Yep, the answer is Antarctica. Way down at the pole, the Earth's magnetic field lines actually dip down and act like perfect, gigantic natural antennas. They funnel these signals from space right down to the surface. It is, without a doubt, the most pristine listening environment on the planet. But, and this is a big but, it's also an engineering nightmare. It is brutally cold, totally isolated, and you're thousands of miles from the nearest power outlet. And this creates the fundamental problem, a real paradox right at the heart of this research. The very instruments you need to do the listening, well, they need power. But the best places to listen are the best because they have a complete lack of power grids and noisy generators. So how are you supposed to power your listener? You see, the standard, gold standard receivers scientists were using, things like the fantastic, awesome system, they just weren't built for this. Not even close. They need way too much power, they're way too big, and they're designed for nice, stable, comfortable labs, not the crushing negative 55 degrees Celsius cold of the deep Antarctic. So the real kicker here is the power. A traditional receiver system, with its computer and all the other bits and pieces, can easily draw over 200 watts. That's about the same as a power-hungry desktop PC. To run that for a year off-grid in Antarctica, you'd need a battery bank that weighs thousands and thousands of pounds. It was a complete non-starter, just totally impractical. This massive challenge forced engineers to just throw out the old playbook. They had to design a receiver from the ground up, with only one goal in mind: radical, insane power efficiency. And their first big breakthrough was a system they called Penguin. The strategy here is just brilliant. Okay, so a normal receiver uses a general-purpose computer. Think of it like a Swiss Army knife. It's got tons of tools, right? But you're only using one or two, and the rest is just dead weight, sucking up power. Penguin ditched that whole idea. It uses a custom, streamlined processor that does only one job: collecting data, and it does it perfectly. It's not a Swiss Army knife. It's a single, purpose-built screwdriver. And the result of that thinking? It's just staggering. A traditional system needs over 200 watts. The Penguin system, while capturing these high-fidelity snapshots of data, averages just 44 milliwatts. That is less power than the tiny little LED indicator light on your TV. What an absolutely massive leap in efficiency. Penguin was a total game changer, no doubt. But it did have one limitation. To save all that power, it only recorded in short 2-second snapshots every 15 minutes. Now, this was great for studying the general ambient environment, but what about those fleeting dynamic events that pop up and disappear? To unlock that next level of science, they needed a way to listen continuously. And this brings us to the next amazing innovation. See, to go from snapshots to continuous recording, they couldn't just improve Penguin a little bit. They needed another revolutionary leap in design. And this was the VLF Advanced Technology Platform, or as they call it, that. The core idea here is so clever. If Penguin's trick was to make the processor way more efficient, that's trick was to remove the processor from the data collection process pretty much altogether. It uses a simple, super-tuned controller to handle all the sampling and recording directly, letting the main brain just sleep until it's absolutely needed. This table right here shows just how big that leap really was. The architecture went from a custom CPU to a CPU-less controller. The power, it dropped again, becoming 5 times more efficient than the already hyper-efficient Penguin. And crucially, look at that last row. The recording mode went from scheduled snapshots to continuous. For the very first time, scientists could have a permanent, high-fidelity ear in the coldest place on Earth. So, all of this incredible, painstaking engineering, just to sip milliwatts of power in the literal middle of nowhere. Why does it matter? What does it actually let us do? What's the payoff? Well, it changes everything, because these devices are now so small, so cheap, and can run for over a year on just a handful of batteries. Scientists can deploy dozens of them all across Antarctica. They can create a continent-wide listening array. This is like going from having a single weather station to having a global satellite network for our space environment, letting us watch how solar storms develop and affect us in real time. The crucial takeaway here is this. By solving a seemingly impossible engineering problem in the most extreme environment we have, we've unlocked a completely new way to explore our own planet's connection to space. And it really leaves you with a final thought, doesn't it? We've built these incredible tools to hear the whispers of our own world. What if, one day, we could place a listener just like it on a moon of Jupiter and hear the hum of a completely alien magnetic field?